All right, so we have so many objectives today, but many of them are just review items. So what you're going to end up doing is to understand and find solution, and I'm going to put a parentheses S, so there could be one or more solutions for a system of linear equations, or linear functions we could call it. So that's our big thing, but embedded in that is to review standard form. We're going to review, well actually let's add to this. Oops. And how to graph using it. Review slope-intercept form. And how to graph using it. And to review solutions of linear equations. Because if we don't understand the solutions, then we're not going to write our answers properly. Okay? So it's a lot of stuff that's review of things we've already covered. And just to let you know, this is coming out of our algebra book, not the online, and this is the first lesson in chapter 8. And that's how they make their marks there. So lesson 8-1. So first off, let's go ahead and define what a system of equation is. And I'm going to make it linear equation. So we are going to talk about inequality equations too. So system of linear equations just happens to be, and you can have multiple equations, but we're going to focus in on 2 equations with the same variables. Now, what are the 2 variables we normally associate with a linear equation? Anyone?
X and Y.
The x and y, right? Something you'll notice in your homework tonight is you're going to see different types of letters. You're going to see A's and B's, you could see R's and S's, but the reality is both equations they give you have to have the same type of variables, and then generally what we do is default alphabetically to write the ordered pairs if we see them, okay? And then a solution to a system of equations is a point or an ordered pair that makes both equations, or let's say, make both equations true. Now the word that you might hear is the word satisfies. Okay, so if you have a point that satisfies both equations, it makes them true, okay? And we could think about it as the point of intersection. Okay, so next, how do we solve a system? By graphing. So this is one of several ways we're going to be discussing how to solve a system is by graphing. And I'm going to tell you, it is the most challenging way in a sense because you need to be most accurate with your graphing. You need to use the blue lines of the graph paper like I've been hounding on you forever and ever. You need to have equal intervals. You need to use a straight edge of some sort so that you have an accurate graph. And you need to draw right through the center of your points. So anytime you don't meet any of those conditions, your graph could be off. So this is very challenging to get an exactly correct one unless you follow all the directions explicitly. And I'll be honest with you, sometimes, and I think there's one question on your homework where the solution happens to be not integers. And how on earth do you disseminate whether that is a half or a third or 3/4 or whatever? That's the hard part. So this is, again, the least accurate way, but we need to know how to do it. Now, if you think about it, this idea comes up in subsequent math classes with a graphing calculator. And there you use the graphing calculator to find the intersection points. So you actually drag a cursor over to where they cross and then find the coordinates there. So this is one of the last times you're going to do it by hand. Okay. So what you're going to do is graph both equations, both. On the same axes. So you're going to get one set of axes, and I'm going to see two lines graphed on top for every single problem of these. Now, I think it probably starts at number 9 where you're going to do that. Now, we've talked in the past in Chapter 7 of how do we graph equations. Well, we could use intercepts. We could use a table, and that's where we picked 3 points for the x's and then calculated the y's. Sometimes if the numbers didn't contain fractions, we would choose 1, -1, and 0, but you could choose any 3 numbers. And the other would be slope-intercept form. So those are the 3 ways we learn to graph. And which way I choose is kind of determined by what did I see, okay? Now, we have 3 occurrences. So if the lines intersect, then the point of intersection, so point of intersection, so it's 1 point, is the solution for the system. Okay? That 1 point satisfies or makes each equation true. That's one thing. Next, if the lines are parallel. You guys demonstrated that with your arms. You notice that they didn't cross. So there is no solution. So I'm going to underline parallel and no solution. So I can either write the words no solution, or I could use the symbol for no solution. Okay? And if the lines, I'm going to teach you a new word, coincide. That means are the same line. There are, and here's the way to write this answer, infinitely many solutions. So what this is saying that's different than all real numbers mean individual values, but these are ordered pairs. So when I say infinitely many solutions, there's an infinite number of ordered pairs that satisfy both equations. Okay? So those are our three scenarios. They intersect, they're parallel, or they coincide. Okay? So let's graph. So directions are going to tell us to solve. And by that they mean what's the solution to this system. So first one, we're going to get two equations, and they're both going to be written in standard form. So if I'm given equations in standard form, I tend to go ahead and do intercepts. And the reason why is it requires the least amount of work. So the whole point behind knowing three different strategies is you got to know what is the best situation. Luke, Michael, which one is the best one to use in the situation that you're given? So to do x-intercept on the first one, you let the y-coordinate equal 0, and we get the x-intercept is -2. And remember, you can write it as an ordered pair. And then to find the y-intercept, I let the x equal 0, and I get y equals -2. And then this one would get graphed at 0, -2. Over here, to get the x, I let the y equal 0, and then I solve for x. So this one required just a little bit more work, so I get x equals -1/2, or -1/2, 0. And then I get the x is 0 minus y equals -1. So I have y equals -1, and then I divide both sides by -1, and I get y equals 1, or 0, 1. So now I bring in my fancy graph paper, and let's see what I need. So again, what you want is to draw your lines straight using a straight edge, a ruler, a very expensive ruler, whatever you choose. Put in your tick marks only on the intersection lines of the graph paper, and then put in at least every other number. So I'm going to graph the left equation in green. So I go to where x equals -2 and y equals -2. And then I draw a line through the two of them. Oops, let's try that again. For some reason I can't always get exactly where I want to go. That's a little better. Now I'm going to do the second equation in blue. And that's where it had an x-intercept of -1/2 and a y-intercept of 1. And what I'm looking for is where did they intersect. And then I have to identify the coordinates of that particular point. So what coordinates would be my solution? So -1 would be the solution. And you can go back and test and plug those coordinates back into the original equation. Is -1 plus -1 actually equal to -2? And the answer is yes. So it satisfies the first equation. On the second one, is 2 times -1 minus -1 equal to -1? Well, we have -2 plus 1. Gives me -1 equals -1. So that satisfies the second equation. So it's the only point that satisfies both of them. Okay? All right, let's try another one. And again, you can choose a different strategy to graph. This one I get x minus y equals -2, and y equals x minus 3. So on this one, I'm going to go ahead and use intercepts. So x equals -2. And then I have y equals -2, which divide both sides by -1, and we get y equals 2. So I'm going to graph -2, 0, and I'm going to graph 0, 2. This one's already in slope-intercept form, so I might as well use that, where the slope is 1, or we can write it as the fraction 1 over 1, and the y-intercept is -3. -2, -4. So left I'm going to do in green. I'm going to go to where, got to add some more. X equals -2. And y equals +2. Okay, and that's that line. Now the right equation I'll do in blue. I go to where y equals -3, and then I rise 1 and to the right 1. And what you see is those lines are parallel and they will not cross. So parallel lines, we can say no solution. Okay. Now, there's an alternative to this one. If one equation is written in slope-intercept form, what if you took the other equation and also solved him into slope-intercept form? What would you notice from that equation that would immediately tell you you're going to get parallel lines? Say it out loud. You would get same slope. Did you get the same slope? So if you notice, slope is 1, slope is 1. That's a verification you're going to get parallel lines. You wouldn't even need to graph it. You would say parallel lines, no solution. That would be your justification for showing work. If you could you could solve these into slope-intercept form and identify that the slopes were the same. Your lines are going to be parallel. Now, if lines are perpendicular, are we going to get a solution? Yeah, perpendicular lines do intersect. Okay? All right, let's do another one. What if we're given y equals x minus 3 and 3x minus 3y equals 9? So this one's already in slope-intercept form, so we get slope is 1, or 1 over 1, and the y-intercept is -3. This one I'm going to do x-intercept, 3x equals 9, and I get x equals 3. Y-intercept, -3y equals 9, divide by -3, y equals -3. So I'm going to graph 3, 0, and 0, -3. So in green, I get y-intercept is -3. Go away, right there. And then I'm going to rise up 1 into the right 1. And then I'm going to graph that. And then in blue, I get y is -3 and x is -3. And what I ended up doing is graphing the same exact line. So what that tells me is that I have lines that coincide. Oh, hell, let me try that again. Coincide. And that means infinitely many solutions. And please don't ask me for an alternative. IMS doesn't work. Don't be lazy. Now, as an alternative, since one equation was in slope-intercept form, and that's an easier way to deal with it, what if I took that equation, that 3x minus 3y equals 9, and I solve it into slope-intercept form? Well, I get this, and I get -3y equals -3x plus 9. Divide everything by -3. And I get y equals x minus 3. So when you compare this equation to the other equation, what do you notice? They are the same. So if you go mathematically and notice you have the same exact equation, then you say lines coincide, infinitely many solutions. Or you can say equations are the same, infinitely many solutions. So there's short ways of getting the answer. All right, let's do one more. We have enough time to get one more in there. So we've got x minus y equals 3, 2x plus 3y equals negative 6. So each one of these, solving for intercepts, would be really easy. X plus 0 equals 3, so x equals 3. This one's a little bit more. 0 minus y, which is negative y, equals 3. I'm going to have to divide both sides by negative 1. And we get y equals negative 3, or 0, negative 3. Here, 2x plus 0 equals negative 6. Divide by 2, and we get x equals negative 3. So negative 3, 0. And then 0 plus 3y equals negative 6. Divide both sides by 3. We get y equals negative 2. So that's 0, negative 2. I don't think we have any positive. No, we don't have any positive y's. So on the left one, the green one, we go to where x is 3, 0, and y is 0, negative 3. And then we have x is, in blue, x is negative 3, and y is negative 2. Oh, look at that. Oops, draw that a little straighter. And what's their point of intersection? They both happen to have 0, negative 3 in common. Okay, so you will be needing graph paper tonight for your homework.